So, everything that moves, from a car engine all the way down to the cells in your body, it all runs on energy. But how does that energy actually get anything done? Well, it turns out energy only really speaks two languages. And today, we're going to break them down. So, let's take that engine, or even a chemical reaction. How do they actually produce power or move something? The answer, it turns out, is always the same. They have to exchange energy with their surroundings. It's the only way anything happens.
Okay, so to make sense of all this, scientists like to draw a little imaginary box around what they're studying. They call it the system. So for an engine, the system might be the hot gas trapped inside a piston. Everything outside that box, that's the surroundings. And here's the kicker. That system can only talk to its surroundings in those two languages we mentioned, work and heat.
All right, let's tackle the first language. In physics, we call it work.
Now, I gotta be clear, we're not talking about your 9 to 5 here. In thermodynamics, work is something very, very specific. It's an ordered directional transfer of energy. Think of it as a coordinated push. Like the hot gas inside a cylinder expanding and physically pushing a piston up. That's work. And this whole energy exchange, it's a two-way street. So when the gas expands, our system, the gas itself, is doing the pushing. It's doing work on the surroundings, and that costs the system energy. But you can flip it. During compression, the surroundings push back, doing work on the system. And when that happens, the system gains energy.
Okay, so how do we actually put a number on this? How do we calculate this energy transfer? Well, believe it or not, the formula is surprisingly simple. And we can actually build it from the ground up, step by step, just to see where it comes from.
It all starts with some pretty basic physics, actually. First, you gotta ask, how much force is pushing on that piston? Well, that's just the pressure from the outside, the external pressure, spread out over the piston's surface area. Easy enough. And what's work? You might remember this one. Work is just force applied over a distance. So, when we mash those two ideas together, we get our starting point for the work equation. But here's where it gets really clever. Look at that area times distance part of the equation. What is that? It's just the volume of a cylinder, right? It's the change in our system's volume, what scientists call delta V. And that is awesome, because measuring a change in volume is way, way easier than trying to track specific forces and distances. And just like that, we arrive at the final, super elegant formula. Work equals negative P external times delta V. Now, you might be looking at that negative sign and wondering what it's doing there. Trust me, it's critical. It's basically a little signpost that tells us which way the energy is flowing. We'll circle back to that in a sec.
Okay, so that's work. It's energy transferred as an organized mechanical push. But what about that other language? Well, that brings us to heat. Heat, which gets the symbol Q, is the other way energy gets around. And it's totally different from work. If work is an organized push, heat is, well, it's a more disordered, chaotic transfer. It's the energy that just naturally flows from something hot to something cold just because of that temperature difference. It's a passive flow, not an active push. And this flow isn't just random chaos. It has a very clear direction. Energy always moves from hot to cold. Always. And it'll keep on flowing until both the system and its surroundings are at the exact same temperature. At that point, we've reached what's called thermal equilibrium. And, well, the energy conversation stops. All right, so now we have our two languages, work and heat. But just like any language, they have grammar. There are rules they have to follow, and we need to understand them. Okay, the single most important rule of this grammar is all about perspective. Everything, and I mean everything, is looked at from the system's point of view. The easiest way to get this is to think of the system's energy like a bank account. All we care about is whether energy is being deposited into the account or withdrawn out of it. This simple idea keeps everything perfectly straight. So if energy is coming into the system, that's a deposit, right? So we call that positive. It doesn't matter if it's heat being absorbed or work being done on the system. It's positive. And if energy is leaving the system, that's a withdrawal, so it's negative. That could be heat it gives off or work that it does on the surroundings. Okay, one last rule, and this one can be a little bit of a mind bender at first. Both work and heat are what scientists call path functions. What does that mean? It means the total amount of work or heat you get depends entirely on how you get from point A to point B, not just that you started at A and ended at B.
The best way to think about this is a road trip. Let's say you're driving from LA to San Francisco. You could just blast up the I-5 freeway, the direct route. Or you could take the scenic Highway 1 along the coast. Now, your start and end points are exactly the same, right? But the number of miles you drove, the work you did, is completely different. It's the exact same idea for energy. The path you take matters a lot.
Okay, so we've got work, we've got heat, we've got path functions, so what? Why does any of this actually matter? What's the big takeaway here?
Well, it all comes down to this. These two languages are literally the foundation of thermodynamics. If you understand them, you can track and control how energy flows. Think about it. Work is that ordered energy, the useful stuff that can actually power a machine. Heat, that's the disordered energy, the stuff that usually just gets wasted and leaks out into the environment. For an engineer trying to build a better engine, knowing that difference, that's everything. And that really leaves us with a pretty fascinating thought to chew on. If you want to design a more efficient system, any system, the game is always the same. You want to maximize the amount of energy that gets converted into useful work and minimize the amount that just leaks away as heat. Learning how to control which language energy speaks, that's the key to, well, pretty much everything, from building better power plants to understanding how life itself works.